So now let's explore the object detection and tracking. In computer vision, it's all about analyzing and understanding images at a higher level. For example, the image you see here are of the same object, a cameraman and his camera. The only difference is that one is rotated and scaled with respect to another, but they contain the same significant structures in each image, which allow us as humans to recognize how they contain the same objects. A computer vision can recognize objects as well by counting mathematical descriptions of important structures. These structures are called features. For example, here is a queen of diamonds. We've identified a number of important features here. The idea is, if we see the same configuration of features in another image, we could assume there is a queen of diamonds in the image. If you can find important features, you can do also sort of cool things, like tracking a person's face as they move from frame to frame. So what do we see in this image? Things like cars, lane markers, trees, etc. We can easily perceive this as humans. But how you would describe these objects to a machine? That's where you need features. Now, that's where you need features. Now, what are features to a machine? So they are mathematical operations that can describe images at a higher level than pixels or zeros and ones. For example, you have edge detection algorithm or corner detection, where you can find the edges, or even more sophisticated and complex algorithms such as SURF and MSIR, and many more. Features can be abstract as they are mathematical derivations from the image. Now, in order to detect an object, you must follow a three-step process where you first detect features, second, extract features, and third, match features. Detecting features means you select regions of an image with unique content. This gives us locations where important content may exist. Extracting features means to compute a descriptor, which is a representation of a feature. This is usually some additional information derived from the local region around the feature that was detected in step 1. Finally, matching features means to find corresponding feature points between two images. With enough features points, you can possibly detect a whole object. The purpose of the detect, extract, match workflow is to arrive at a geometric transform between the original image and the target image. This requires you to find as many matching points as possible. Features are important key points in the image, which could be edges, points, or objects. There are many different techniques which give unique capabilities such as rotation, scale, illumination, invariance to features. Another advantage of working with features is they represent compact information about regions in the image. Depending on the application and feature properties, we will choose the feature extraction method. If we consider every individual pixel as features, it will be very dense features. Other feature extraction techniques which are sparse in nature are the HOG, the histogram of oriented gradients, which computes the oriented histograms from blocks in the image. SURF, feature extractor, which is invariant to rotation, scaling, and to somewhat illumination. And also bag of words features, which stores image as visual words, and many others. Well, to maintain the history of object motion, a detection algorithm has no way of knowing that the object is found in frame n is the same as the object found in frame n+1. So you can't make a prediction about where the object might be in frame n+2. Detection is computationally expensive. And as we get into high resolution full motion video, you can rely on slow detection to keep a real-time space. You can rely on slow detections to keep a real-time pace. Tracking algorithms don't need to find an object. They just need to follow it. So there is less work to do. Here you see a tracking in action. So you see you are not detecting again, we're just following the features in every frame of the image, in every frame of the video. So far, in all our examples of object detection and tracking, we had a reference image of the object, which we could compare to a new image, which allowed us to detect the object. But in many cases, object detection is done without a reference image, such as license plate recognition of vehicles at a toll gate. In these cases, the reference image is replaced by a model. A model is a representation of a certain object that has been learned by a computer. These models typically come from AI algorithms in machine learning and deep learning.